All right, our next speaker is Shane Jensen. Shane is Assistant Professor of Statistics at the Wharton School at the University of Pennsylvania, where he has been teaching since completing his PhD at Harvard University in 2004. He's an avid baseball fan and maintains an active interest in sophisticated statistical models for the evaluation of player performance. So thank you, Shane.
Thank you, Mark. Thank you, of course, for the invitation to speak with you today. I'm going to be talking about, I assume everybody can hear me. I feel like I'm projecting. I'm going to be talking about one specific aspect of baseball and modeling player performance, and that is in the realm of fielding, which is one of the sort of more, as I'll explain, one of the more difficult parts of baseball to measure. So the overall goal is accurate evaluation of fielding performance for every Major League Baseball player. Obviously, this is, again, a somewhat underexplored, though there are many people working on it now, aspect of the game. And part of the reason for that is it's one of the harder parts of the game to quantify. You know, things like hitting or pitching are more easy to tabulate and quantify because they typically consist of mostly discrete events that can be tabulated and quantified easily, finite number of outcomes, finite number of base runner configurations. The only really continuous aspect of the game that I'm going to be discussing today is fielding. And so here it's a much more of it's sort of a greater data and modeling challenge because you are taking into account a playing surface that is continuous and how players are interacting on that continuous surface. You know, and obviously data availability is another issue that we're going to sort of have to confront very quickly, in fact. So, yeah. Feel free to interrupt with any questions if I start going too fast, or if I go too slow and you want to speed me along, that works too. Okay, so what am I sort of competing with, or what are other methods that are out there? I mean, most people who do any research in baseball have heard of the ultimate zone rating. Essentially what this consists of is it's not modeling the field as a continuous surface. It's basically discretizing the field into chunks. It divides the field into large zones, and then you tabulate successful versus unsuccessful plays for each fielder in these zones. Okay. The probabilistic model of range, which is done by David Pinto, is somewhat similar in the sense that it's sort of the field is now cut instead of these sort of zones. It's pie slices every 5 degrees from home plate, and the same sort of thing. You're again tabulating within these zones. So both methods, obviously, I've only used the word continuous about 20 times already, have a similar weakness. They're discretizing the field of play. And my approach is going to be trying to, as much as possible, treat the field of play as the continuous field that it is. All right. So a weakness of UZR or PMR is that each zone or slice is large, and that sort of limits the ability to detect small differences between fielders. Of course, there's inherent noise in the data, so you're not going to want to necessarily, you wouldn't want to take, just shrinking the zones wouldn't be necessarily the right approach. You're going to want to smooth over the field, so you kind of smooth out these sort of stochastic differences from season to season or from player to player. Okay, so that's essentially what I would like to do. What I need to do that is as high a resolution data as possible for fitting these continuous models. Makes sense? Luckily enough, well, I mean, it's sort of a chicken and egg thing. I wouldn't be presenting this if I didn't have the data, but luckily enough, I did actually acquire the data for doing this kind of model. Baseball Invo Solutions is a company that essentially measures this type of data, and we were able to get their data through a grant from the kind folks at ESPN. And we essentially, what we have is 4 years of data from 2002 to 2006. Of essentially the XY coordinates of every single ball in play onto the field of play for those seasons. It breaks down, in case you're interested, into the various components: 42% grounders, 33% flies, 25% liners. Each ball in play is essentially mapped to a much smaller area. That's the whole point. Than the UZR zone. So basically, we have a resolution of approximately 4 feet by 4 feet. You might wonder how this is actually done. Apparently, it's a person with a laptop in the stands that's essentially marking on the laptop where the ball lands when it happens. So that's the pixelation of that is where you get the 4 by 4 sort of resolution.
A top foul ball is a ball in play?
A caught foul ball is in fact a ball in play, yes. Though we get rid of them, so for these purposes, no. for this talk, no, they're not. But yes, in fact, they are. They're coded in there. All right, so obviously the velocity is also measured, though not measured again as you would ideally want. Velocity is measured as a category, 1 being, very softly hit, 5 being very hard hit. Like all, I don't know, any survey sampling people out there? When you give people a category between 1 and 5, what do they pick? 3. So something like 90% of the balls are actually categorized as 3. Takes away a little bit of the information, I would say, but, again, we deal with what we have. And again, this data, I don't mean to disparage it because it is clearly better than anything else out there. So here's what it might typically look like. There's technically 2 colors on that plot. There's fly balls that are caught in red and not caught in black. A little bit hard to see, but essentially this is for a particular center fielder in a particular year. This is the type of thing we'll be modeling. Is what is the distribution of the probability of making a successful catch versus not. And once we have that sort of a good idea of that distribution, we can start comparing players, which is obviously what we got into this for. Okay. If the ball caught is the center fielder's contribution, that's easy. Not caught, there's a shared consequence thing that you can estimate. I'll talk a little bit about that. So several of those not caughts would also show up as not caughts for the left fielder and right fielder as well. Caught is easy, obviously, but yeah. Okay. So essentially, this high-resolution data allows us to fit smooth curves to the continuous plane surface. Just as sort of an illustrative example, and we actually do use this later on. I will describe how. But this is sort of, if you just use sort of a 2-dimensional kernel density smoother to smooth out the dots you saw in the earlier plot, you get these sort of distributions for singles, doubles, triples, and home runs. Home runs less interesting from a fielding perspective, but present in the data, and kind of make a cool plot. Obviously, the plot for triples is what I think is the most interesting. That you get this sort of the much more asymmetric. Though all these plots are actually asymmetric, if you were to look and sort of measure contour lines and stuff like that. But the triples are obviously the most striking, just because the throw from right field to third base is a lot longer. So that's what powers that. And also, I should mention that, the basal info solutions people themselves have their own sort of system that is based on their own data, but does not use this sort of smooth curve approach. And I don't know if anybody out there has the fielding Bible, but that is what they produce. Okay. All right, so what is our approach? Well, our approach is called SAFE. It is a spatial aggregate fielding evaluation. I have to credit Kenny, my collaborator, for a pretty sweet acronym. Essentially, what we're going to do is we're going to fit a smooth curve to the average fielder in each position. All right? And that essentially consists of basically aggregating all center fielders together, estimating the probability of success of each of a ball play sort of as a function of distance from traveled and velocity and all this other information that we have. We're going to fit that smooth curve for the average fielder. And then we're going to fit that smooth curve separately for each individual fielder. Okay? And that's going to give us 2 different, curves that we can compare, an individual fielder versus the aggregate. And I'll use the words aggregate and average pretty much interchangeably. So step 3 is calculating the difference at each point between the average curve and each individual curve. So you can, again, think of these, in the case of outfielders, these 2-dimensional curves. You just calculate the difference between them. Then you want to weight those differences by the ball and play frequency so that, a fielder that shows a higher probability of catching a ball where balls are frequently hit is rewarded more. And you also want to take into account run consequence. And so we're going to have a couple different weighting functions for weighting by ball and play frequency and run consequence. And then we're going to put it all together. We're going to aggregate, sort of integrate all these differences between curves weighted by these various things. We're going to do numerical integration to calculate an overall value, which is essentially can be interpreted as the total runs that a particular fielder saves or costs his team in the field. And this very sophisticated mathematical formula at the bottom is supposed to just summarize the basic ideas. There's some, missing integral signs and stuff like that, but let's not get too crazy. Okay, so how do I actually do this? All right, so obviously we have different ball and play types that we're going to have to treat differently. Flies and liners in the outfield, for example, are a two-dimensional thing that we have to model. And so success depends on both the distance and the direction of the ball in play. And so flies and liners, you can imagine, is this sort of ellipse here where you've got where the fielder is standing and the distance he has to travel to the ball in play location. So, again, I'll show you more specifically what the curves look like a little later. Grounders are a little bit different. So the way we treat grounders is actually to sort of treat them one-dimensionally. So grounders, the way the data actually results is the grounders, if the grounder is successfully fielded, we have basically the location where it was fielded. If the grounder is unsuccessfully fielded, we have the location where it was picked up by the outfielder. All right? And so we essentially have to project that back to where essentially the infielder missed it. And so we're basically projecting grounders onto this one-dimensional line essentially, which is the left or right direction and distance that the infielder has to travel to try and get that ground ball. And so we essentially do infield grounders as a function of sort of angle. So angle across the plate, angle from the home plate that the infielder has to travel from where he started to where the ball is actually fielded, or not fielded, as the case may be. Okay. Excellent, excellent, excellent. All right, so I keep talking about these smooth curves. What do we actually use for these smooth curves? We're going to use logistic functions. I'm sure logistic regression is something most people in this audience have heard about. We're going to essentially model let's just handle grounders as an example. Essentially, the probability of making a successful catch is modeled with this function of angle and velocity. And so the log odds of making a successful catch, which is what we have on the left-hand side, is a linear function of the angle and the velocity. And the actual equation is a little bit more complicated because we're going to use different coefficients on angle whether we're moving to the left or the right, which again makes sense. You're going to want to take into account the direction because, the glove's only on one of the two hands. Logistic function for balls and fly balls and liners, a similar thing, except of course we're now using distance instead of angle, so distance traveled, sort of a radius out. Again, we have velocity in there, and we've got a different coefficient on distance whether you're moving forward or to the back. Okay, so again, we're trying to acknowledge the fact that running 20 yards in front of you to make a catch is maybe a different entity than running 20 yards behind you to make a catch. Yeah.
So we're working under the assumption that the fielders start in the same place?
Haha. Good question.
I'm not measured, but that's the assumption?
That is the assumption, yeah. So essentially what we're going to do is, what's sort of hidden in all here is we have to essentially fit a centroid that basically is defined as the center fielder starting position. And so to a certain extent, we'll see later on, when someone comes out as a good fielder, there's a bit of a confounding in there. We don't actually know if they're a good fielder because they're really fast or because they're, a little bit better than average at positioning themselves. To a certain extent, that's kind of mixed in there. As far as who's a good fielder or not, it doesn't matter, but that we are kind of confounding those effects together. Yeah.
Do you ever have a problem with the fact that if the ball lands right where the center fielder is, the chance is probably so close to 100% that's going to throw off the loose?
No, just because there's so much. I mean, you do certainly see, the curves certainly bear that out, but there's enough data away from that it doesn't, the curves are very stable in that respect. You do kind of get some crazy stuff actually with players with small sample sizes, which I'm hoping I'll have time to talk about, but for any player that we actually sort of care about, that is not an issue. Okay, so let's just have a look at what some of these average things look like. Here's the infield essentially. We get, this is again viewing the infield as an angle from third base onward, so we get this sort of wide swath of players. The curves are essentially at the point with highest success probability, and as I just mentioned, each distance is actually an estimate since we don't know exactly where the fielder was standing at the start of the play. And again, the curves are allowed to be different moving to the left or the right. All right, and we can see sort of what a typical, sort of difference between the curves might look like. So here, for example, is 2005 Shortstops. The black curve is the average shortstop. The red curve is Adam Everett, who we sort of found to be the best shortstop by our measure, and by pretty much every measure you want to take. He's very good. And Michael Young was found by us to be the worst shortstop. And you see actually a pretty dramatic difference between the curves. Again, how much that difference means in terms of runs saved and costs is something we're going to have to get to. But there's a pretty noticeable difference even just looking at, I mean, these are the most extreme examples, but just looking at one position, there seems to be quite a bit of signal there. All right. Here's what the curves look like, for example, in the outfield. So here's Darren Erstad on the right in 2005, or probably, actually, maybe no, 2000. Darren Erstad in one of the years. And then on the left-hand side is the average curve for center fielder's probability of a catch. This is a little bit more subtle to see, but if you do notice, is this the laser? Oh, yeah. Right. No, the other thing that looks like a flashlight? There's so many flashlight-like objects up here. Maybe I will. Perfect. Okay, so you see up here, for example, you do sort of notice between these two curves that there's a lot more flatness at the top of Darren Erstad's, implying that Darren Erstad is getting, in balls hit near to him, he has a higher probability of having a catch. And you also see down here, you sort of notice that there's a difference in height. So it seems like Darren Erstad is sort of dominating this average curve. Out here, he's getting to a higher number of balls at a fair distance out. Obviously, I don't have the scale on here, but that's a fair distance out. Okay, so that's essentially what we're dealing with. And now, of course, the whole point is to take the difference between those curves, and for example, for shortstop or for third base, this is kind of what the difference is, what I mean by the differences. Here's, say, for example, our aggregate third base model. Here's the black curve. Here's the blue curve, which could represent Alex Rodriguez. I don't think this is actually, I think I just made this up. This is not his actual curve. And the differences, obviously, you take between the two is just the point-by-point difference. So, for example, at the zero angle, which is, right at third base, there's a negative difference in the sense that the average third baseman's catching a lot more balls than A-Rod is hit right to him. Probably not actually. Again, this is made up. But out here, it seems, at least in this synthetic example, A-Rod is actually faster or has a greater range than the average third baseman, so he's actually getting more balls out at this particular angle. All right. And so, again, we have differences here and differences here. Not all differences should be treated equally. If there's a lot more balls hit here than there are here, you want to weight that way. And the same thing with the run consequence of those balls. So, for example, weighting by ball and play frequency is pretty easy. I mean, that's what those density estimates I showed you at the start are. We have a density estimate of the ball and play frequency for the entire field. All right, and we can weight our tabulation by that so that more frequent distances or angles are more important. Here's just an example of the overall density for fly balls in center field. And you see sort of, a little bit of asymmetry left versus right. And you see, again, the sort of direction that they're going. There's a little bit of multimodality as well. Kind of cool. All right. Very nice. Run consequence is another thing we want to weight by. So run consequence is something where, not all missed catches are created equal. If you miss something in the power alley, that thing's going to be rolling for a while. You're going to end up with a triple or something like that. So, for example, here, just looking at the outfield, here's the run consequences of liners to different parts of the outfield. Again, this is home base up here. And you do see a real spike at the power alleys, where if you happen to hit a liner out there and it is missed, you're going to be running for a while. And same thing with ground balls. So you get sort of a nice little thing in here where there's a real sort of, depending on the velocity, so velocity 3 is harder hit than velocity 1. And for harder hit balls of velocity 3, you see that at the sides, right up basically on the lines, you have a real spike in run consequence, which again is not surprising. Every single ball that a shortstop, ground ball that a shortstop misses is pretty much a single. Right? Because the left fielder's going to be there, and if it's not Manny, he's going to catch it and throw it to the logical place it should go, and the guy's limited to a single. Right? But down the line, that could be a double, or in the case of over here, you could have a triple. And in fact, that's where a large number of triples, in fact, occur. Okay, so we want to take that into account. And so you get this nice little kind of trade-off. Because shortstop is considered typically a more, defensively oriented position than third base. Because the ball and play frequency to shortstops is so much greater than to third base. But balancing that is the fact that the third baseman, when he does miss something, it typically is of higher consequence in terms of runs. Okay. So there's that interesting kind of trade-off. So let's just put it all together quickly with an example. Yeah.
What if how do you account for errors? Like if the guy makes the shortstop makes the play, but
Again, this is all fitted smooth curves, right? So no individual play ever sort of like is at. So errors are sort of kind of on top of all this. So I mean, basically, we're measuring kind of this smooth thing smoothed and averaged over the entire season. So you want error or not, it does not sort of come into our model in any kind of dramatic way. I mean, the errors are in our fitted data, so an error would count as an unsuccessful play, certainly by the way we're coding it. So for example, the vast majority of unsuccessful plays hit right to the guy would also have been simultaneously coded as errors. Okay. So here's an example. Again, I think I've been kind of going through this somewhat logically, but say Carl Crawford has a 95% probability of making a catch to a particular point in center field, some point in center field. The average center fielder has an 85% probability, so that gives Carl a positive difference of 10%. You want to weight by the ball and play frequency, so if Carl sees 15 balls in play that hit there during a season, that means he's actually basically making a successful play on 1.5 more balls in play than the average center fielder. How many runs is that going to be worth? Well, you want to take into account that ball, the run consequence of that ball in play, which is going to be a weighting of the ball in play density for the singles, doubles, triples I showed earlier. Just basically layer all those on top and kind of calculate the proportion. And that's all well and good. And let's say the run consequence is 0.65, you multiply it out, and he's saved you almost a run at that point. Synthetic example, typically the totals aren't actually that high for any one point, but anyway. And so aggregating Carl's run values then across all the points gives us the total run saved or cost for Carl. Or for anyone else, really. Okay. Let's just quickly go through some results. These are also all, I'm going to give you my website link at the end of the talk. These are all up on the web. You can check them out yourself. And we, I don't know exactly what I can say here other than the fact that, most of the things look pretty reasonable. Doug Mankiewicz seems to pop up to the top of all these sort of measures as being an amazing third baseman. Nobody can be surprised by Jason Giambi being pretty poor. That's not a shock to anyone. Second baseman, same thing. Robinson Cano, the Yankees have a real infield. All right. Third baseman, one surprise, Mike Lowell doesn't do well by us, which as a Red Sox fan, I'm surprised by just because he seems to actually be pretty good, but whatever. Scott Rowland is the best third baseman, or at least he was. Adam Everett, again, I showed you already earlier, was the worst shortstop. Best shortstop, Michael Young was the worst. Our measure, in the continuing controversy over Derek Jeter, we come out on the side of him not being such a good fielder. Outfielders, I know, kind of hard to see. Just a couple of surprises here. No surprise with Bernie Williams and Ken Griffey down in center field. Aaron Rowand and Nuke Logan are up there. Coco Crisp, very good in left field. Trot Nixon, really good in right field. I'm kind of hidden in shadows, but this is my eyebrow kind of going up in a quizzical way. I don't know why that is. And good old Willie Montagna, not so good in right field. Or in any field you put him in, actually. Okay. All right. We can also compare, again, it's a little bit hard to compare our results to anything else, because there is no, it's harder than doing, say, prediction of hitting, because there's no truth. We don't actually have a gold standard to a certain extent. But we can at least look at other measures, and we do have decent overall agreement between SAFE and UZR, which again I would still consider the industry standard. We can also look at correlation between years to see if we're at least capturing signal that is consistent for a player across years. That's obviously, again, confounded if a player really does change over time, then what are we measuring here? I don't even know. But anyway, looking at the correlation and comparing sort of between UZR and SAFE, we seem to actually do better for most of the infield positions and a couple of the end right field. We do actually not so good for first base. First base seems to continue to be somewhat of a problem for us, but we're still working on that. And I guess I'll just sort of summarize what I've done thus far. Maybe I'll talk for like 2 minutes about a really interesting extension. Essentially, again, our model-based approach, we have a smooth probability function that I think actually really reduces kind of the variance in our results, because you can share information between all points in the field. All right, we have this nice run value that puts these individual differences we calculate on an interpretable scale, which I think is very nice. And obviously, in our year-to-year correlation, we compare favorably. Finally, I just want to talk about, because it comes back to the question that was asked, when you have small samples, some of these curves can get a little crazy. And so, for example, let's just look. These are small samples for some players lead to highly variable estimates. So these are the fitted curves for the top, like the 100 center fielders or whatever in 2000, or the 100 people who played center field at some point in 2005. And the aggregate is the black line. You can hardly see in the individual ones. Tons of craziness. So this guy here, I can't remember who it is, but goes out. He's pretty much perfect, way longer, and then he just drops off. It's like he falls down at 30 yards every 100 yards every single time or something. I don't know. I mean, I can guess who that might be, but I wouldn't want to guess. Or this guy here, who, I mean, this is nice and all, but probably a little bit kind of crazy. I doubt that this, got like Ben Johnson out there in the right field or something. I don't know. Anyway, okay. So what we can do is basically what's driving this is we're fitting our hierarchical model completely separate, or we're fitting our SAFE model completely separately for every single player. The only sharing that comes in is on the average curve. And the logistic functions are fit for each player completely separately. But you kind of want to maybe, for players where you don't have a large sample size, to share information, because players aren't that different. So we want to accentuate the small differences, but share information for players where we have a small sample size. And a hierarchical model is a great way of doing that, sharing information between parameters that you're trying to estimate. And so we can fit a hierarchical model to this exact same stuff, and that's what these red curves represent. So these red curves are the same players that have been fitted with a hierarchical model, and basically the effect you get is that their player parameters their curves are shrunk in towards the middle a bit. It basically shrinks in some of these crazy estimates, and so that you've got a more reasonable sort of spread of curve between curves here. All right, so that is our approach, and I think I will stop there.
Professor, maybe one or two questions.
Yeah.
How do you kind of get if at all for double plays, like in terms of like as a shortstops and second base and first base like that? I know it's partially related to.
Well, we have in the data who actually fielded the ball, and if there's any outs, it's a successful play. It's coded as a successful play. So whether or not like once he fielded it, it goes on to be a double or triple play is to a certain extent not relevant to us. Yeah, so arm is not in here. I have another paper on throwing if anybody's interested as well, but our arm function's not all in here.
On the logistical equation, the variable for velocity, is that just simply coding, fast or,
Yeah, it's from 1 to 5. It's 1, 2, 3, 4, 5.
Have you ever considered trying to construct a proxy variable for hang time using all the data about the distance from home plate and the various other coding that BIS include?
Yeah, so actually that's interesting. We actually had sort of, in one formulation I remember, we actually had distance from home plate and to the ball, and then I think, yeah. I mean, the short answer is yes, you could do something like that to try and get a hang time.
I saw your presentation given
Yeah.
at Penn, and there we have the radius of that variable, which is obviously linear. The fire arc go, the harder it is to catch the ball. Then you have a distance vector from home plate, and then you have like different things for like whether it's a fly or a pop.
Right. So that, yeah, that's right.
I was just wondering if you could basically construct, if you've given the parameters for speed, trajectory, and distance from home plate, you could get a proxy for hang time, and that would move linearly with the distance, the radius from the center.
You could, I mean, we've looked at, as you mentioned, we've looked at that briefly. We should look at that more, actually, because obviously hang time is kind of the big proxy variable you're trying to get at.
Two more quick questions.
Is there any sort of ballpark adjustments?
Well, that's sort of the slide I skipped over. So, currently, no, in the sense that when we do the ball and play density, we're doing just sort of the overall ball and play density across all parks. One could envision doing the ball and play density for individual parks. I mean, a couple complications. Those would be higher variable densities because there's a lot less data, and it's only the play. Obviously, only half the time is that actually contributing to any particular fielder. But we've looked at it in a few different cases, very specific cases like Fenway. Obviously, is a very funny little park. And so, for example, when Manny came out absolutely terrible by Safe, we looked to see how much the wall had an effect on that. It turns out even with taking into account the wall, he's terrible. Great hitter, though. Anyway.
Did you have any way of dealing with home run balls that could have been caught?
No, we certainly haven't looked at that yet, but that would be something interesting to do. I mean, we presumably could. Again, that would definitely, you'd have to be very specific about the ballpark specific, dimensions and all that stuff. But that would be a cool thing to look at as well. Definitely.
All right, let's stop there if you have any other questions.